Okay, well, good morning, everyone. First of all, are there any questions before I start? Okay, well, I would encourage all of you to attend our colloquium today at 4 o'clock. My former student, Professor Bo Yuan, will be here to give the talk on deep learning accelerators. So definitely that's a great topic. If any of you is interested in doing project on that. Let me just say what our plan today is. So our main objective today is to begin chapter 2 on iteration period bound, and then I will try to probably stop after 20 minutes or so, and then Nanda, who is sitting here, will spend the remainder of the class on Verilog. So this is kind of supposed to be an intro for you, and I know that it is very natural that many of you have questions about what you need to turn in, where you need to turn in the Verilog assignments. So we'll get to all of those slowly. We'll try to create an upload link for the Verilog part in Moodle. It doesn't exist now, but we'll get to that maybe next week sometime, certainly maybe next week, Monday, Tuesday, something like that. So a lot of you that have questions on Verilog may be able to get the answers that you want. So by all means get started quickly, because it's certainly well, it's certainly not going to be easy if you have no practice before. Okay, so I quickly was going through this so-called noble identity in multi-rate systems. So one of the noble identity is if we have this xn, then we upsample. Well, let me write that in a new page. Okay, one noble identity So basically that's saying that if we have the Z transform here, which is XZHZ, and then you whatever the inverse of that is, you expand by factor of m, that means you have m minus 1 zeros. So clearly the Z transform of this will be XZ to power mh Z to power m, which is exactly same as the Z transform here. So these are equivalent. So there are two noble identities when you begin to analyze multi-rate systems, one involving expanders and one involving decimators, but that's the expander noble identity. So what it says is that if we were computing, if this is our desired computation, then by expanding by factor of m means that we are interleaving m minus 1 zeros. Okay, so that's kind of what I talked about briefly last time. So okay, so I guess okay. So in any case, the idea of interleaving. So if I have let's say xn going through a filter h of z, and we are computing yn, and then that says that if I change every delay by, let's say, 4 delays, so every delay d replaced by 4d, wherever you have one delay replaced by 4d, then we take x0, 0, 0, 0, x1, 0, 0, 0, x2, etc. And that says that we will now be able to compute y0, 0, 0, 0, y1, 0, 0, 0, y2, etc. Now, so these zeros, so this is perfectly computing correctly, but these are null operations. That means this hardware is sitting here without being fully utilized, and that says that if I had multiple 4 different time series to be filtered, then I could take this as x prime 0 and replace this by x double prime 0 and replace this by x triple prime 0, and then I can have 4 different time series. So instead of having one time series and then 3 null operations, then we can have 4 different filtering operations interleaved in the same hardware. Okay, so that's what I went over that quickly. Okay, so we have completed the concepts of pipelining, and we have talked about interleaving, and those all are in the context of feed forward circuits, circuits with no feedback. And we saw that any time we have a feed forward circuit, circuits without feedback, we can pipeline those by adding delays at appropriate feed forward cut sets. However, when there is feedback, then the circuits have a fundamental iteration period bound. So we briefly talked about this before, the so-called iteration period bound, which is the maximum of all loop bounds. And we talked about what a loop bound is, and a loop bound is the loop computation time divided by the number of delays in the loop. So if we have a loop that has computation time 100 and has 5 delays in the loop, so that bound will be 100 by 5, which is 20, and you then take all such loop bounds, and then we can find the iteration period bound. So the iteration period bound is a fundamental bound So this is a fundamental lower bound on the iteration period, or if you want to think about that in single input, single output systems, clock period. So clock period or for single input, single output systems. Okay, so so sometimes it's useful for us to know what that fundamental bound is, because that is for a given technology and given library of circuits, that's a fundamental bound. So you cannot really achieve an iteration period less than that bound, no matter how you try to pipeline, parallelize, whatever you try to do. So sometimes it's useful to, before you start designing, it's useful to know what that bound is. Okay, so now how do you compute that bound? If we were to design an algorithm to compute the iteration period bound, well, we can't use the definition. Why can't we use the definition? Because the number of loops in a data flow graph can grow exponentially with the number of nodes. So that said, we need to find polynomial time algorithms to compute the iteration period bound. So the goal here is not to find algorithms that take exponential time with respect to the number of nodes, but to find polynomial times. So there are a couple of algorithms in chapter 2 of the textbook. One is called the longest path method, and the other is called the minimum cycle mean method. So I will well, let's see if I can get to at least one of them, and maybe We'll talk about the other one in the next class. So the so-called longest path method to compute the iteration period bound proceeds like this. So let's take the IIR filter. In this case, I will take the example from the textbook. So this is a fourth order. This is all pole, means there is no feed forward part or the numerator, only the recursive part, because there are 4 states, 4 delays. It's called fourth order. More number of states is 4. Number of states is 4. That's the order of the filter. Okay, so let's assume that the multiply takes 2 time units and adder takes 1 time unit. That's the example from the book. So, so if you look at the 3 loops here, the inner loop and the intermediate loop and the outer loop. Okay, so the loop bounds, if I call this L1, L2, L3, then TL1 is going to be 2 plus 1 plus 2, that's 4 by 2. TL2 is going to be 2 plus 3, 5 by 3. TL3 is going to be 5 by 4. Okay, so then the iteration period bound, which is max of all of these, 2 and 1.666 and 1.25, which is going to be 2. So 2 units of time is the iteration period bound, and the inner loop is then called the critical loop. This is called critical loop because that loop's bound is the iteration period bound, and that means I can say that the intermediate loop here is a slack. Slack means that's the time I can delay, and that's I can play with a little, and we'll see how to exploit slack in a variety of ways to reduce power consumption, to reduce leakage power and all kinds of things. So it's nice to always have some slack no matter what you are doing. So 2 minus 5 by 3, which is 1/3, and the slack of the outer loop is 3 by 4. Okay. Okay, so that's great for an example, and in most of the times in your exams it's easy to compute these things. But how do we then use this longest path matrix method to develop an algorithm that can compute this in polynomial time? Okay, so so the first step is to compute a flow graph. Let's call these nodes as D1, D2, D3, D4. So there are 4 delays. Then I create, so each delay corresponds to a node. So each delay corresponds to a node. Okay. So 4 delays are now mapped to 4 nodes. Now what I want to do, I want to compute the longest path. I want to compute the longest path from, so compute longest path from node I to node j such that the path does not contain any delay element. So, so that's the first step. The first step is to so essentially the best way to think about this. So, we want to compute the longest path so that it does not contain any delay element. So, so we can say, okay, well, the first thing we can say is what is the longest path from D1 to itself? How can I start with D1 and come back to this itself so that I don't go through any other delay? Well, that's not possible. If I am sitting at D1, there is the only way that I can come back to D1 is to go through D2 or any number of delays. So, so we can say that the longest path from 1 to 1 and doesn't exist. There doesn't exist a path. Okay, what about 1 to 2? From I can go from D1 to D2 with there is nothing being computed here with critical path 0. So, the longest path from D1 to D2 is 0. So, we can it's easy to go from D1 to D2 without computing anything. What about D2? Okay, anything else? I can't go to. So, while I am doing this, I can also write down. Let me write down this so-called longest path matrix. So, these two are equivalent information L1. So, L1 well, we need a little more space. We can start here. So, 1, 2, 3, 4. So, L1 is -1, 1 to 2 is 0. I can't go from 1 to 3 or 4. So, -1, think of that as a symbol. That is not a number. So, think of -1 as a symbol. So, if I am at node 2 corresponds to D2, delay 2, I can come to D1, I can from D2, I can get back to D1 with 4 time units. Okay, so that's 4, 2 to 1 is 4. So, we can also put that 2 to 1 is 4. 2 to 3, any volunteers from longest path from 2 to 3? 0, good, very good. So, 2 to 3 is 0, 2 to 4, you can go 2 to 4. Okay, so, so 2 to 2 you can't go. So, 2 to 2, 2 to 3 is 0, 2 to 4 is -1. Okay, if we are at 3, I can go to 1 and I can go to 4. 2 plus 3, 5. 3 to 1 is 5 and 3 to 4 is 0. 3 to 4 is 0. 3 to 1 is 5. Okay, and if we are at 4, 4 to 1 is 5 and that is it. Okay. So, 4 to 1 is 5 -1 -1 -1 and 4 to 1 is 5. Okay. So, that is our this is our L1 and we will see in a minute why I am talking about L1 because we will compute L2, 3, 4 etc. So, this is the first longest path matrix L1 and we need to compute as many delays. In this case there are 4 delays. So, we will need to compute from L1, compute L2 and then compute L3 and then compute L4. If there are 100 delays then well compute up to L100. Okay. So, any questions about okay, how we compute this longest path? I will talk about that probably next class. Okay. And read Appendix A. Appendix A talks about 2-path algorithms, Bellman-Ford algorithm and Floyd-Warshall algorithm, which are 2 of the algorithms that can find longest paths. So, the Bellman-Ford algorithm finds longest path from one node to all other nodes, whereas Floyd-Warshall finds all pairs of longest path algorithms. We will talk about that. Okay, so how do we use L1 to compute L2. So L1, we can use L1 to compute L2. Okay, this is how we compute L2. So to compute L2 ij should be max of L1 ik plus L1 kj max over all k. So that's essentially saying, so let me give you an example. Let's say I want to find L2 22. So I want to find L222. So L222 will be maximum of L121 plus L112. So that's the longest path from 2 to 1, and 1 to 2, that's the longest path from 2 to 2, and L2 2, well, okay, plus L22. So that's essentially going through. If there is a loop, okay, if there is a loop, 2 to 2 is a loop, and if there is a loop, you go through that twice, L23 plus L31. So go from 2 to 3 and 3 to 1, and L24 plus 41. So go from 2 to 4 and 4 to 1. And in all of these, we will keep the -1 as it is. So if that means there does not exist a path. So we can say what is L21 plus 12, L21 is 4 and 12 is 0, so that's 4 plus 0. 22, L22, 22 is -1, so that's just -1 is not really a number. I mean, just forget about it. So that path doesn't exist. 2, 3 is 0, 3, 1 is 5, so that's 0 plus 5, which is 5. 2, 4, that's -1. I don't need to worry about that. So -1 means, well, that path doesn't exist. So this is now 4 and 5. So then we get 5. So so if you continue through that, let me just show you. Well, you can continue through that. So if you go through that process, L did we make a mistake? L2, where is the? Yeah, something doesn't seem right.
L32.
L, yeah, 32, yes, okay, yeah. I am glad you are all watching because 2442, yes, okay, very good. Okay, so 2, 3 plus 3, 2 doesn't exist, so this is -1, so that doesn't exist. So that just becomes 4. Okay, so thank you. So please correct me so that we make sure that we are not making mistakes here. Okay, so you can compute L2 and then so how do you compute L3? Well, to compute, we can use L1 and L2 to compute L3. So for example, L3 of the L3 matrix is 3k plus k3 over all k, and this says here k maximized over all k, but it shows here k is 1. I guess that means there was only one path, others were -1, which means so go through that L3, and L1 and L3 can combine to L4, and then so we can get all these things, and then so we can compute all these matrices. So compute L2, so L, for example, L3, compute L3 is computed from L1 and L2. Okay, so so finally, the iteration period bound is defined as L 1 I divided by I L okay, by 1 L 2 by 2 up to L D I by D maximized over all I. So, what we are saying here is that you take all these L matrices and so for example, L2 and look at the diagonal elements. So, let us say this is A, B, C, D, then these candidates are going to be A by 2, B by 2, C by 2, D by 2. If we take L3 and let us say these candidates are E, F, G, H, then that will this L3 I by 3 will be E by 3, F by 3, G by 3, H by 3 and so on. So, why is it that we are dividing these by this in L2 we are dividing by 2, we are only taking the diagonal elements and we are dividing that by that number. So, what does that really mean? It says if, so think about what the physical interpretation of these diagonal elements are. So, so if I go to, in this case it so happens that all the diagonal elements are -1, but if I go to L2 let us say, so if I, so what does L2 compute? L2 computes the, if I start from 2 and come back to 2, if you start with 2 and come back to 2, that says the longest path starting with 2 and coming back to 2 is go, so we start with 1 delay, we go through 1 more delay, that is 2 delays. So, L2 diagonal entries are going to be longest paths such that you start with any node and come back to same node by going through 1 more intermediate node, that means a maximum of 2 delays. That contains the critical paths of all loops containing 2 delays. L3 will contain the critical paths of all loops containing 3 delays. Why? Because I start with 1 delay and then I go through 2 intermediate delays. So, I go through this and then that, okay, I can't come back. So, that is not going to be possible. So, so when we do find L3 such that the diagonal entry is not -1, that means we found a loop containing 3 delays with a critical path. So, if we take the diagonal elements of all these L1 to LD and then divide them by the whatever that, if it is 1 loop, then that is the critical loop containing 1 delay. If there was a self loop, that would be the diagonal element in L1. Okay, so okay, we will talk more about that. I will stop here. We will talk more about that, and we will talk more about why the time complexity of this will be order of dE. So, if there are d delays and E edges, I can compute L1 in that time complexity plus d fourth, where d is the number of delays and E is the number of edges, and this d fourth is the time to compute L2 up to LD. So, this is L2 through LD. Each L computation takes order of d cube because it is a matrix multiplication containing d squared elements. Each element contains d operations. So, I will stop here. So, you can come and connect your computer. Okay, so we will talk about one more method. Read chapter 2 and appendix A. So, Nanda will go through cadlab. How many of you are not using cadlab now? Okay, few of you. Okay, so well, you can remote login, and the handout we gave last time has the name of machines. Where is the physical lab? They can go there and.
I think it's 2120.
Okay. So please ask questions to him. He knows everything that you need to know, Verilog. Okay. So you can sit down and continue teaching the remainder of the class.
And there's a clip over here. Keep it outside so that the signal is not blocked. And keep this mic facing upwards. Okay.
This is not showing on the screen because you are not connected.
It's still my laptop.
It's not connected. You can sit down and feel comfortable.
Please let me know once you're done so I can turn it off.
You have not logged in yet.
No, it's still powering up.
Why you are supposed to be ready? Before, what were you doing for when you were sitting here?
The battery had actually died, so I had to power it up.
Okay. What?
He'll turn on the mic once.
That's fine. You are using HDMI or?
HDMI, yes.
Oh. So maybe in the interest of time we may skip some of the initial slides.
Sure.
Just go to the slide that talks about students can read some of the introductory slides.
Sure.
But, we'll start with the one first syntax.
Sure, I'll do that.
everyone hear me? So these are all the files which have been uploaded to the Moodle website. So so the first one will actually tell you how to access the machines if you want to log in remotely. And I've also added a couple of scripts for you to run. The dcflow is to run synthesis, and the run file just lists the command for you to run on the terminal to run simulations on the machines, right? So, and also for your reference, I have provided a system Verilog file for the FIR. So that can be used as a basis to develop your FIR implementation for a 5-tap system. So right now it's designed for, it's a parameterized block which you can set it either as 3-tap or 5-tap. And for this demonstration, I've actually set it up as a 3-tap system. So to start off, this presentation will be a tutorial on how do you use Verilog and system Verilog to design. And this is meant as just as a refresher, and also for those of you who have not seen Verilog coding before. For those who have taken the 5327 class, which is VLSI Design Lab, a lot of this content may feel similar to that. And I've tried to cover as much as possible, as well as try to cover a few topics in system Verilog for design as well. So in general, Verilog is used as a language to design. It's a hardware description language to write out digital designs, from very small designs like this case, in this case, an FIR filter, to complex designs like a million-gate processor. And this is basically done in an efficient way such that it allows for, let's say, easy development with tools that can understand this language and interpret it and derive different sorts of hardware designs from that. So just I'll skip directly to the actual design elements. So this is actually an example of what a Verilog code would look like. So the basic unit of Verilogs are modules. So the module basically is used to define a hierarchy within your structure. So you can think of it as an aggregation of very similar set of functions whose ultimate goal is to take a set of inputs and give a set of derived outputs. And a module is what encapsulates this entire functionality into a single block. So what is shown in this slide is how you actually write the syntax for these kind of blocks. So for example, in the very first line, you actually have the module name. The next the lines 4 to 8 talk about what are the port declarations. So every module needs to define what are its inputs and outputs. So whenever we design Verilog modules, you need to think of it as actually designing physical pieces of hardware. So in case you design a module, think of it as you're designing a black box where the inputs and outputs are the in-outs for that design, and the contents are the contents of the module. So in this particular case, for your FIR, you have defined that you have a clock pin, a reset pin, a pin to take the coefficients for your FIR, and you have 2 data buses to take your input data and a data bus to give you your output data. So one thing which Verilog and System Verilog allows is for parameters. So in general, when we have these sort of designs, in most scenarios, not all factors of the module will be fixed, and they can be modified to suit different needs. So in this particular case, the width of the data bus is not actually a fixed quantity, but here can be parameterized to can be parameterized to, let's say in this case, a width of 8. But then this will depend on what are your requirements. If you have any sort of a system which has a very stringent requirement on the noise, signal to quantization noise ratio, then you would want to experiment with these data widths to allow for like a lesser quantization noise in your design. So wherever possible, it is a good practice to parameterize in any part which you feel that would change in the later courses, or which you would need to modify to meet some design specification. So in this particular case, the widths are parameterized, and even the number of taps are parameterized. So once we have defined the parameters for the design, we need to actually define the ports which we have declared. So how will the tool actually know what are these? Are you able to see my mouse? Yeah. How will the tool actually know what are these ports defined as? So how will the tool know, for example, that your data, your input data is actually a bus and not a single wire? And that is where the definition comes into play here. So in the definition, we actually state what is the direction, what is the type of the wire, type of the data, as well as in this particular case, whether it's a signed data or unsigned data. And lastly, here is where we define the width of the bus. So in this particular example, if you see the input data, we define the data as a bus of width data, as in it's a bus of width data width. So in this particular case, it's an 8-bit bus. So this is very similar to your C style of coding, where you define arrays, and even in Verilog, the numbering convention starts from 0. So if you want to define an 8-bit bus, you have to define it as 7 down to 0. So how this convention works is, Verilog has two types of arrays, packed arrays and unpacked arrays. So everything which is to the left of your signal definition is called a packed array. So packed array in general define things as physical quantities such as buses or memories, whereas quantities which are actually on the right, the unpacked elements, represent more as a number. So the way to think of this is, you should understand how the tools synthesize these codes into actual hardware. So when a tool actually sees this sort of a coding style, let's say for example for the coefficient, it will interpret that the coefficient is a bus of width 8, and there are n taps such buses. So in this case, there are 3 buses of width 8. So this is what this sort of a coding style in Verilog indicates. So in general, you just need to understand like what is packed arrays, what is unpacked, and then in which circumstances do we use each one of them. And lastly, like we defined any internal signals which we need to use. So it's generally a good practice to define any signals used, like how you would in C, if you want to use integers or doubles, you define the internal variables as int or double. The reason being is that if you do not define these quantities, by default Verilog takes it as a wire type, which is a single bit type. And if you intended it to be a bus type of data, you will run into a lot of issues when you're actually designing, but then you'll never know why this happened. And Verilog by default has like an implicit definition. So even if you have like small typos in your code, it will try to think of it as a new variable, and it will try to work along with that, and it assumes that it will be a 1-bit wire design. So that talks about like how modules are made. So in this kind of a design approach, we look at it as a hierarchical kind of a view, where where common modules are combined together to create higher functionalities. For like the most common example is like if you have like this sort of filter, you can have multiple filters in parallel which do different operations, like a low pass. This can be act as a low pass filter. You can in parallel have a high pass filter, and so on and so forth. And this actually shows you how you would instantiate modules within other modules. So always module defines some sort of a code block, and within modules you can instantiate other sub-blocks as you would normally do in codes, right? Think of similar analogy would be like functions in C programming. And in this particular scenario, you can connect your modules in two ways. One is either you can connect by order. So in the same way as you think of like a function definition, you can either just place the inputs in the correct order. The other option which it gives is a connect by name, where you explicitly define which pin the wire goes to. So in this particular example, the names which are outside the brackets will match the names which you have defined in your port declaration over here. So you can see that this list here matches all the list over here. And the names within the bracket are the names of the buses or wires which are at the top level module. So in a sense, what we are stating in this is, if this is contained within another module, for example, we are connecting the top level clock to the internal clock of this module. And similarly, we are connecting the data input from the top level module to the data input of the like the sub block here. So, if you guys have any questions or doubt, you can always stop me and ask. Right? So one important aspect for those of you especially who have not used Verilog before and are new to hardware design languages in general, Verilog is entirely a concurrent execution. So traditionally, when you look at C codes or software kind of programming, you think of codes as a set of statements which are executed in sequence. The way to look at Verilog codes is each module is by itself a parallel thread, and every module executes in parallel. So you can never guarantee any sort of ordering between different modules unless you explicitly give some kind of control to ensure the ordering, unless you have some sort of like a handshake signal to tell that, okay, now this module is done, proceed to the next module. Because by default, all modules execute in parallel at the same time, and the best way to imagine this sort of a situation is imagining that every single module is a parallel thread. And this is not just for modules. As we will see later on, Verilog has something called always blocks, assign statements. These blocks also behave as concurrent executions. So in general, it's a very important thing to consider, because this is a very common source of mistakes, because most people do not account for the fact that these blocks execute in parallel. So they lead to a lot of conditions where they are called race conditions, where the output is not known because the two competing modules are trying to drive this output at the same time, right? So you'll not know the state of the output. So coming a bit into the actual syntax in Verilog. So there are three very commonly used data types. There are more data types available, but these are the most common, and these are the ones which you will see most of in designs. So wire data types defined as nets, and register data types are defined as variables. So the reason Verilog has these two types of data is that it's trying to mimic real life hardware. So in hardware, there are two types of connections you can have. Either a wire connection, which is just a passive connection between two different, let's say, two different circuits, or it can have a register which can store data within your design. So by having a net data type and a variable data type, Verilog tries to incorporate this sort of a mechanics within your coding, so that the designer can try to code as much as possible as what they intend the design to be. So there's actually a lot of confusion as when to use wires and when to use registers. And in general, if you're kind of new to Verilog and new to system Verilog, you can probably just use the logic data type. Logic data type was introduced in system Verilog just to remove the amount of confusion you have in wires and registers. And in most scenarios, logic can directly replace both. So if you're getting a little bit confused about when to use wires, when to use registers, probably logic is your safest option. All right? So another important aspect which Verilog covers and which essentially models all of digital design is the blocking statement and the non-blocking statement. So as the name implies, a blocking statement just states that all execution is blocked till this statement completes. So, and it is basically this assignment operator here. So the way to imagine it is that unless the assignment is complete, you will not actually proceed to the next set of statements. This is kind of how you would imagine combinational circuits work, right? So for example, an AND gate, as soon as an input is triggered on an AND gate, the output is immediately triggered. So that is kind of what this blocking operator tries to recreate, any sort of combinatorial logic which instantly reflects the output instantly reflects the state of the inputs. Whereas the non-blocking statement is more designed to how flip-flops operate. As you know that in a flip-flop, there's a certain delay between when the clock edge comes and when the Q pin of the flip-flop toggles. So, and because of this delay, if there are a cascade of flip-flops, the data will not be captured on the same edge as which it was driven, and is always captured on the subsequent edge. So that is how delays are modeled within your system, like within Verilog and system Verilog. And in this particular case, this non-blocking operator tries to mimic that behavior. So in the case of a flip-flop, if you imagine that there is a positive edge which comes, it will evaluate all the inputs at the positive edge, but it will drive the input only after the positive edge has completed, in a way to mimic the behavior of how a flip-flop behaves, right? So I hope that the difference between like a blocking operator and non-blocking operator is clear. And I
find it non-intuitive. I mean, I would think the first one would be called non-blocking, the second one would be called blocking. Yeah. I find the naming non-intuitive, whoever named this.
So the naming convention is based on how it behaves in the code. So if you have a sequence of code and you actually write it with the blocking operator, it will not proceed to the next step unless this line completes.
Okay, I see. Yeah, okay, that makes sense. Okay, go ahead. Yeah.
So coming to the next slide, we are going to talk about like the different types of hardware which you can synthesize using Verilog. So this is not meant to be an exhaustive list, but just to give you a rough idea of like the scope and capability. And you can always try yourself to explore and try to design different sort of modules and try to synthesize them and see how Verilog synthesizes the codes you write. So for combinatorial logics, I wanted to actually show you the 3 types of ways you can actually design in Verilog. Namely, you can design it either as structural blocks, as a data flow model, or as a behavioral model. So what does all of these mean? So yeah, let's look at this. So when we talk about structural models, we actually break the design into its corresponding gate level design. So for example, let's take the example of a simple 2:1 mux, which has a single select line. So we all know that this is the Boolean expression for the 2:1 mux. So in a structural design, you would design this as an actual sequence of gates which are chained together. For example, you get the inverted of S by this gate, then you have 2 AND gates to combine these 2 results, and then finally an OR gate to give the final output. So this is how you would imagine, like how you design structurally. And data flow is similar in the sense that instead of designing it at the gate level, we can design it with Boolean expressions. So if you have the Boolean expression for a system, you can assign it in this manner with, so assign here is a keyword which you can use to assign assign different values. So yeah, and finally we have the behavioral model. So this is as close as it gets to C type of coding, where you, rather than actually designing it in terms of Boolean, you actually write down the logic as you would imagine it or as you would write it down. So there are advantages and disadvantages to each, whereas in the case of like structural, you actually define the structural in the most optimal way which you can imagine it. Data flow is kind of in between in terms of optimization, and behavioral is usually non-optimized and you leave the entire interpretation to the tools. So there can be advantages there as well as disadvantages. So in this particular case, we can see that for a simple 2:1 mux, it just boils down to a case statement. And it need not be a case statement. You can even write this as, let's say, for example, a if-else statement. So the only condition for a mux is that you need a completed design, as in all the if should be complete. If you're testing a 2-bit value, you should have 4 conditions which are tested. So this is an important characteristic because when we talk about flip-flops and other designs, we'll go over like how does the tools actually differentiate between combinatorial logic and actual flip-flop logic. So continuing with like more examples of actual combinatorial logic. So this is an adder and a multiplier which is designed as like a pure combination, as a pure combinatorial logic. So here we are actually using a behavioral model to design this. If you require, you could also try to do it by a data flow by actually using like inbuilt, like trying to use like well-known multipliers like a Booth multiplier. But in this particular case, the tools are smart enough to understand that when you have these sort of operations, that it will internally design a multiplier based on the requirement. So the only things which you need to be careful about when you make these sort of designs is especially how the data widths are handled within the tools. So for example, if you know that when you multiply 2 8-bit numbers, the final result will not be 8 bits. It will actually, the number of bits will increase to 16, right? So in this particular case, when you define these output variables, you need to ensure that the widths that you define, for example, this multiplier output, can handle the total output given by this multiplier. Otherwise, you will lead to, like, there will be certain errors in your design. And these are very common sources of error when you do Verilog design, because the tools do not know that you intended to actually, whether you intended to truncate the result or not.
But you should be able to do that in another line of code. Keep
Yes.
15-bit result, you can keep, say, 12 bits.
Yes.
In one more line of code.
Yeah. Yeah. As Professor stated that in these kind of scenarios, that you would want to have the ultimate control of which bits to keep with you. So you, in this particular scenario, you would take the multiplier to the full precision that it allows for, and then in another line of code actually select the bits which you require to keep. So for example, in the 16-bit output, if you do not require all 16 bits, but you want to again truncate it back to 8 bits, you can do that in the next line. And for signed numbers especially, it's important to keep note of sign extensions. So in System Verilog, they actually have the facility to do sign extensions with typecasting, which was not there previously in Verilog. So this is something which you should make use of, especially if you're doing any signed operations. So the last block which you're going to talk here is about flip-flops. So in general, a flip-flop is similar in design to the combinatorial logic, but instead of having an always at the rate star block, so what I forgot to mention is that when you have always at the star, the paths within the bracket actually talk about the sensitivity list. So star indicates that anything in the block is part of the sensitivity list. So in case like if S changes, A changes, if S changes, A changes, or B changes, this entire block will be triggered to get a result. Whereas in the case of a flip-flop, as you'd imagine, your output should not be triggered unless you get a clock or a reset. So for example, this actually models a active low reset positive edge triggered flip-flop. So when we want a positive edge triggered flip-flop, we use the keyword pause edge with the clock. And when we want an active low reset, we actually see the edge in which the active low reset triggers. So we say in this particular case the negative edge. And the first line we actually have is the reset condition, where when the reset is, in this case active low, we define what would be the desired outputs. And then when it is not in reset, this, like as I mentioned before, the non-blocking operator mimics the flip-flop operation. So ultimately, when the synthesis tool looks at this code, it interprets it as a flip-flop like this.
Is there a data flow model for a flip-flop?
Sorry?
Is there a data flow model for a flip-flop?
You need to actually keep it within an always block, because in this particular case, like the non-blocking operator will only work in the always block. It will not work in an assign statement. And in terms of data flow, if this is a simple flip-flop, but you can always combine a data flow model here by actually driving the input based on some data flow object. So for example, instead of driving just directly the D pin, if you want the input to be like the AND of two signals, so you could write that as, let's say, for example, A and B here in this line here. Right?
Yeah.
I hope that answered your question. Yeah. So as I mentioned before, that there's some, it's almost very similar between like combinatorial logic and like a latch based or flip-flop logic. So what System Verilog has introduced is they have introduced these keywords called, like in this particular example, let's say for example always underscore FF, which explicitly tells the synthesis tool that you should interpret this only as a flip-flop and nothing else. So this actually brings in all errors to the compile time itself, in case you do not write a code which can be interpreted as a flip-flop. And similarly, it has introduced this called always underscore comb, which indicates to the synthesis tool that this has to again be interpreted only as a combinatorial logic. So in general, when you have memory within a block, so a synthesis tool, it detects memory based on whether there's any condition which cannot be uniquely determined by the inputs. For example, if you, in this always block here, if we had like only one of these conditions filled, and let's say the second condition was not filled and there was no default statement, so the synthesis tool will actually interpret this as a memory, because if, for example, S is equal to 1, it will just hold the previous state. So this is how memories are designed within Verilog. Any sort of if condition without an else condition, or any case statement which is incomplete. So any input condition which is not defined here, under those input circumstances, the synthesis tool interprets it as a memory and will hold the previous state. Right? I will just skip over the finite state machine, but this you can go over it yourself. It explains how do you design finite state machines as a two always block design, and it's an extension of, it's a combination of both your combinatorial circuits and your flip-flops. So, and also for testing, I'll just go over it quickly, is that, so for testing, there are various methods you can test this. You can either design very simple test benches in Verilog to just see the core functionality, or those of you who have taken like the advanced verification course or the lab course can see that you can design extensive test benches which does something like random testing or exhaustive testing of the design. And I will not go too much into detail about the testing, but we will provide you like a small circuit for you to test with, and also we'll try to provide a circuit so that you can exhaustively test your design. So this was the, oh, I think I have the wrong slide. I don't have the, so now what we can do is I can just go through a quick example of how you would run this design on the VLSI CAD machines.
Are you seeing, you may have to put the HDMI or something, we can't see.
Okay.
Or your computer is not on yet.
It's on, it's not sharing the screen.
Put the HDMI on the
Yeah. Is everyone able to see the screen now? Yeah. So for your simulation, we have actually provided a couple of files here. So in this particular case, we have provided a small FIR test bench, which in this scenario just drives a set of input, like in this scenario defines a fixed set of coefficients and drives a constant input on the data bus, but then you can modify this to test it out and try out more design, like whatever scenarios you would like. And also we have provided a small run file that lists out what is the command which you require to run this design. So in this, so an example of how you'd run this file is if you make this file executable, you can just call it on your terminal as so, and then you can run the simulation like this. So .simb is the Synopsys default output, and just the GUI option allows you to have a graphical display. So this is your actual design, and then in general you can dump out all the variables here and then run the simulation. So if there's any particular value you'd like to see, for example, this is your design under test. So this is your input data, your clock coefficient. So like here you can just add it to a new waveform. And is it visible to get everyone in the back? Okay, yeah. And as you can see that initially we drive the coefficients and then the data. And as the input data is processed, you can see that with each clock cycle, the FIR updates based on the calculation. So one thing to note is that some of you may be wondering, like, what is these numbers here? What is 20, what is C0, and what is 10? So these are all in 2's complement representation. So for example, you can set the radix here to 2's complement, and then you can see what are the values given here. And another thing to note is that when we actually have these values, we have set it in as a fixed point representation. So where these numbers do not directly map to what an integer number would be. So if, for example, this is an 8-bit number, so you usually have a number of the range of let's say 127 to minus 128. But in this scenario, how we interpret this bus is, let's say, for example, the high MSB bit will be the sign bit, and it is assigned to, in this particular case, to the value of -1, and every subsequent is a lower power of 2. For example, the first bit is 2 to the power 0, 2 to the power -1, 2 to the power -2, 2 to the power -3, and so on. So in this particular case, when you see the value is 20, this is actually 0.25. Similarly, this is in 2's complement, so I've just made it as a signed representation so you can see it. So in 2's complement numbers, this would be C0, and C0 internally is -0.5. Right? So this is the number representation we have used, and an important thing to note is that these sort of scales are entirely defined by the designers. The tool does not understand that actually that this is to be interpreted as a 0.5 or as a 0.25, but these are defined by the designer based on their requirements, and the designer can choose where to place the fixed point to decide what is the scale of these values. And yeah, so that's a bit about what this thing is. And as you can see that once you have, let's say for this example, if you have an FIR such that the first and all your date pairs is in this case 7F. So 7F times 20 gives you FE. Then in the next cycle it will be 7F and then 7F times 20 minus 7F times, in this case, minus 40. So your net result should be 7F times minus 20, which as you can see here is minus FE here, right? FE0. And lastly, you will have what do you say, 7F times 20 minus 7F times 40 plus 7F times 10, which will basically be just 7F times 10, and you can see that the final, so 7F times minus 10. So you can see that the final result here is like minus 7F times 10, right? So this just gives you like a brief overview of like the water testing tools which are available, how we use VCS. To just again just give a brief look at how we will use the synthesis tools. So when we have a synthesis tools, we need one main file, which is your Synopsys DC setup, which tells you what is the actual libraries which are being used in this particular scenario. So for example, we say that in this we are using the SAD32 library, which will be the same as which you are using in the VLSI design lab if you have taken that course. And we are using the RVT library for typical with a 1.05 volt supply at 125 degrees Celsius. So this is how you actually interpret this library notation. And this library, if you actually read this part, there are multiple standard cells available which you can work in either low VT range, high VT range at different either fast corners, slow corners. But for the purposes of this class, we've just shown you for the typical corner, so you can focus more on the design aspects than just improvements based on the technology. So this is your how the structure of your workplace will look like. You just have to make, the only thing which you'll have to modify is in your Synopsys design, you need to point to the correct path at which you are working. So in my case, it is in this path here. So you have to set up your files as follows. Like in your working directory, you have an inputs folder which contains the constraints and the RTL. So in this particular scenario, RTL is just a single file for FIR, and your constraint contains what are the different constraints on your design. So in this particular scenario, since we have a very simple design, the main constraints are only, the main constraints target the clock definition. So in this particular scenario, you're saying which pin in your module actually corresponds to the clock, what is the frequency of the device, and what are the input and output delays which you want to keep as boundary conditions. And from this, we have provided a script that goes through the basics flow. So this script again is very similar to what you have done in VLSI Design Lab. I'll not go over it in detail, but if you have any questions, you can always approach me or send me an email and I explain it to you. But in general, the script essentially analyzes the RTL blocks and tries to find the design, in this case the FIR block. It elaborates and compiles the design, and we can just quickly see how we would invoke this command. So for example, the tool which we are using is the DC shell, which is design compiler by Synopsys.
We have run out of time. Maybe wrap up in 1 or 2 minutes.
Yes, I just finished this the synthesis. It runs quickly. Oh, sorry, I'm just running from the wrong directory. So as you can see, the script actually is designed to handle the entire synthesis process in the background, and you do not need to give any inputs from your own end. And all the outputs are dumped into a reports folder, but if you require, you can always report, like say for example, the timing. So since this is a 100 megahertz clock, that means your clock period will be 10 nanosecond. And we can actually see that the total time which has propagated from basically the start to the end. So in this particular scenario, this is your worst case delay from register to register. And this is going to be very less since in our design it just registers cascaded. But let's say, for example, if you see for the output pins, you can see that there's a significant delay of, like here the delay is 2 nanosecond. So this is how you actually read these results to see like what is the critical, what's the critical path in your design, and basically what are your constraints for your design. I think that's probably it. And if you want to require this, if you want to see the schematic of the design, you can always start the GUI.
Power, area, those things.
Sure. So similar how we have report timing, we also have commands for doing report area, which will tell what is the total area of the design. So in this particular scenario, since it's only a synthesized design, it will tell what is the total cell area. And similarly, we can also have a report, we have report power, which tells you what is the total power consumed by design. So for example, in this case, the 3-tap FIR filter consumes 54 microwatts of power. So you can always use the man command to see more detail about these commands and what is used internally, and also these reports. And by default, the tool will also, the script dumps out all these reports into the reports folder here, as seen. Right. Okay. Thank you, everyone.
Well, I would say start playing with this. Don't wait until next week, Monday, Tuesday, it will be late. So start today.
So you'll have to so the professor asks you to do Verilog codes. So for the results, you need to basically verify that the FIR functions properly. So we are trying to give you some sort of so that you can test it in a more realistic scenario. And with that, like once that is up, okay, we'll send out.
So test bench will be given.
Yeah, so this basic test bench already exists, so you can test out your design with that. And you can give you another test bench, which will be more exhaustive. So that maps onto more than the test bench which I just showed you right now. So when we actually give you another test bench that will have like specific